In the 18th century, a French mathematician asked, "What is the probability that a needle will fall in between two parallel strips of wood on a floor if the needle is dropped?" His name was Buffon, and he found out that the probability of the needle intersecting two strips of wood could be used to calculate the value of pi. In this video, I will show a demonstration of Buffon's needle experiment, and I will also mathematically prove the problem. For Buffon's needle experiment, you'll need a piece of paper, something to write with, and something that can simulate a needle. To start off, you are going to line up the needles or toothpicks back to back, and you're going to draw a line. I already had the lines pre-drawn to make the process faster, but you'll do this until the end of the paper, and once you reach the end of the paper, or as far as you can go, you'll move on to the next step, which is you'll gather more needles, and the more needles you have, the better the estimate will be to pi at the end of the experiment. So I already have 50 toothpicks, and I will scatter them randomly on the piece of paper. All right. Now what you'll do as the next step is you'll count the number of needles that intersected the lines that you have drawn. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? Yeah, 15 toothpicks that intersected. And the probability of the needles intersecting one of the lines is equal to 1 over pi. And you will learn this later on in the video through the mathematical process. The probability can also be written as the needles that intersected, so needles that are intersecting the lines over the total amount of needles. Now this will equal 1 over pi. And if you flip the equation, so you'll get total amount of needles divided by needles intersecting the lines. That will then equal pi. So the total amount of needles that are on the paper that I scattered around is 50. So this is the total. And the number that intersected, as I just counted, was 15. 15 toothpicks intersecting. Now, if I plug that into a calculator, I'll get 3.33. And this will be the estimate of pi. And as you all know, pi is equal to 3.14. Okay, so now we will calculate Buffon's needle problem mathematically. First, we'll calculate the distance. When you drop a needle, it can fall at any particular angle on the paper. To start calculating the distance, or how far the needle is from the closest line, we will measure the center of the needle to its edge. We can draw a circle around the needle and use trigonometry and what we know about the unit circle to find the angles at which a needle intersects the line. The radius of the circle, or the hypotenuse of the triangle, is equal to 1/2 because the center of the needle to the edge of the needle is 1/2 of the needle. The leg opposite the angle is equal to sine theta, but because the radius of the circle is 1/2, the leg is equal to 1/2 sine theta. And now, 1/2 sine theta will also be equal to the distance between the needle and the closest line. Restrictions on the distance. Assuming that the lines on the paper are 2 units apart, the distance between the needle and the closest line can be 0 units away if the needle is intersecting, and at most 1 unit away because the needle has a length of 1 unit. Restrictions on theta. We can use what we know about the unit circle and say that the angle that is formed will be an acute angle in the first quadrant because there will be no negative values associated with the problem. The distance cannot be negative because the needle will always be some unit or some measurement away from the line. Thus, theta is greater than or equal to 0 and less than or equal to pi over 2. Finding the probability. Now, we will find the probability of the needle intersecting a line. In our case, the probability will equal the area under the curve over the area of the window or rectangle of the graph. We can graph the equation of d equals 1/2 sine theta to see where the needle can reach if its angle is adjusted. The graph will look like this. The area under the curve is a shaded portion of the graph. How do we solve for the area under the curve? First, we will set up an integral. Integrations are used to find the area of figures with curved sides and edges. We can set up the integral by using the function for the distance, finding its antiderivative, and evaluating it from 0 to pi over 2, which is a restriction on theta. We can then simplify the equation by using the integral property that is shown. Next, the equation can be further simplified by converting the sine theta into its antiderivative, which is negative cosine theta. And then we will plug in the pi over 2 and 0 into the antiderivative and solve using properties shown to the top right of the screen. After fully simplifying the equation, the area under the curve should equal 1 over 2. We will then be finding the denominator of the probability equation, which is probability equals area under the curve over the area of the graph. So now we'll be finding the area of the graph by multiplying the length and width of the graph that fits the restrictions together. As you can see on this screen, the total area of a rectangle equals length times width. The length of the graph is the distance axis, which is 1. That's the max it can go up to. And the width, the max the width can go up to, is equal to the theta axis, which is pi over 2. Again, that's the max restriction on theta. Then you'll multiply the length and the width together, and you'll get 1 times pi over 2, which is equal to pi over 2. So pi over 2 will be the total area of the graph. The final step will be to add the values found into the probability equation. So you'll put the area under the curve, which is equal to 1 over 2, and you'll divide that by the area, or total area of the graph, which is equal to pi over 2. And you'll end up with a probability equaling 1 over pi. Now, how do you estimate pi? The probability can be seen as the number of needles that cross the line, x, divided by the total number of needles, n. This is another way of finding the probability as shown in the experiment. If we put this into a math equation, 1 over pi, the probability we just figured out, is equal to x over n, which is the same as flipping the equation and getting pi equal to n over x. And that is it for today's video. I hope you guys learned how to estimate pi using the Buffon's needle problem and experiment.